Okay, so we are going to take some notes today on work and power. So let me get my screen shared for all of you. Here we go. So I know I have these printed out. Those of you that are absent, you're going to want to write them down. That's what we did here in class. I just have them printed out just so that these notes don't take forever for you and you can kind of pause it and write it down at your own pace. And the graphics are a little bit more helpful than what we had in class here too. So we have a couple new concepts that were introduced today since we just wrapped up forces, took our forces test yesterday. So that is something too that you might have to make up depending on how many days you were absent. Now, the definition of work is very different in physics than it is in our everyday life. Work is the product of a force times the magnitude of displacement. So work is factoring in how much force is required to move something. It's only done on forces that are parallel to displacement. So the entire force needs to be parallel or in the same direction, same line as the displacement. So how that force causes something to move, or a component, a portion of it. So work can be done at an angle, but only a portion of that work is completed, the part that's completely parallel to the displacement. So a man pulling a girl on a cart, causing her to move forward at an angle, a component, a portion of that is considered work. And so work is done on forces that occur at an angle. If I apply a force to the right on the left side of the box to try to push it to the right, and then the box actually moves to the right, that's directly parallel, so in line with each other, so work is being done here. Or if I was doing the opposite, I push from the bottom to try to move the box up, and then the box actually moves up. So I'm applying a force upwards, box moves upwards, that's parallel with each other as well, the same direction. So when work is not done, you can see this little comment here, this is a great pay for not doing work, is when a force and displacement are perpendicular to each other. So here this person is applying a force upwards on the tray, but moving forward with the tray. Now work is being done on their arm as they're moving the tray up, as they apply a force up and then they move the tray up. But as soon as they stop moving upward and then walk forward with the tray, then no more work is being done. So once their hand is stationary, applying a force upward, but they move forward, then we have no work when they're perpendicular or at a direct right angle to each other. All right. Our work equation, so work is a product of force and displacement, so we're just going to multiply force and displacement together. And if there is an angle, then we're going to throw in a cosine of theta for that angle. Our symbols and units. So the symbol for work is a W, so that'll make it easy to remember. It starts with the same first letter as in work. Unit, though, is a little weird. So the unit is a J for a joule. So you pronounce it like a jewelry jewel, but it's spelled a little different. Force, symbol for force is still F. Unit for force is the Newton. And remember, your weight is considered a force. And so your weight is also going to pop up again with these problems. Displacement, symbol for that is D. And you can think of that as the distance that something moved for the most part. Unit is in meters. Another formula that we're going to work with for this unit is power. Power is a way to describe the rate that work, or you could also think of it as energy transfer, is being done. Our power equation, since it's a rate, you're just taking the amount of work that was done over the time that work was done. And we can figure out then the rate that the work was completed. We call that power. You might have heard power in everyday terms, talking about horsepower in a car. Symbol for power is a P. Unit for power is a W, a watt. And how I like to remember that, electrical power is also measured in watts, and wattages, that's how you get the power value for your light bulbs. That's where you would see power in our everyday world. Your 60-watt light bulbs, for example, or 100-watt light bulbs. And then work, W, unit J, and then time, T, unit seconds. So I have a few practice problems that we're going to do here together. And then your homework that is posted is we're going to be working with these practice problems here as well. Let's see. So we want to do, I have written down here, we're going to do number 1 here together. 1, 2. All right, so with number 1, we have a child runs with a balloon at a 21-degree angle with 1.5 newtons of force. The child pulls the balloon 13 meters. How much work does the child do on the balloon? So I do have the child runs with a balloon at a 21-degree angle. So I do have a theta here, an angle in degrees. So we'll write out 21 degrees for that. With 1.5 newtons of force. So force here is 1.5 newtons. The child pulls the balloon 13 meters. So meters, that's a unit for displacement. How much work does the child do on the balloon? So in this case here, I'm looking for work. So looking at my formulas, if I'm looking for work, I want to use the work equation. So work is force times displacement. And since I have an angle here, I'm going to throw into a cosine of theta. Since our angles are given in degrees, we do want to make sure that our calculator is in degree mode for these problems. This is a nice plug and chug problem here. So work is going to be the force, 1.5 newtons, times displacement, 13 meters, times the cosine of the angle. So the cosine of 21 degrees. So 1.5 newtons times 13 meters times a cosine of theta. So that should give us 18.2. And if I'm looking at my sig figs here, everything is 2 significant figures. So I can just round that down to 18. And the unit for work is a J for the joule. That's just kind of a straightforward work problem. Let's now look at one that we have a couple, since power is the rate at which work is done. We do have a couple what we like to call 2-part problems that like to pop up here and there in this unit. So let's do one of those, since those are a little more complicated. So here I'm looking for what is the average power supplied by a person with a weight of 591 newtons that is running up a flight of stairs a vertical distance of 4.11 meters in 4.2 seconds. So starting off here, it's asking what is the average power. So power in this case is an unknown, something that I'm looking for. I have a weight of 591.0 newtons. So if we remember from our last unit, W, in this case, a lowercase w, that'll help us distinguish it from our work. 591.0 newtons for the weight is running up a flight of stairs, a vertical distance of 4.110 meters. So I have distance, again, if it's just a straight line motion, your distance is the same as your displacement. So that's the displacement here, distance of 4.110 meters. In 4.2 seconds. So my power equation is work, not weight, over time. So I can't use this W to go up here because this W stands for work and this W here stands for weight. So I have time, but I don't have the value for work yet. So I actually have to, this is a two-part problem, I have to solve for work first, get that number, and then I can plug that number into my power equation. So work is force times distance, and I don't see a cosine of theta here, so I'm going to leave that out. If you did do that, you could just use cosine of 0 if you want to just habitually use the cosine of theta. So here I have displacement, and right now I might go, well, I don't have force, what can I do? Well, remember, weight has the unit of force because weight is a force. So your acceleration is just gravity, so it's a special type of force. So I can use this weight number as my force value, because this is a force. This is the force felt on the person's body due to their mass and gravity. So I'm going to use the weight to solve for the work. I'm going to use the weight as my force here. So 591.0 newtons times 4.110 meters. So we got 591 times 4.110. So that gives me 2,429.01 joules. So I'm just going to use the 2,429 here. All right, I'm going to make this a little more uppercase here because now I have found my work that's being done. So this work is how much the force of their weight is being displaced as they're going up the stairs, so a combination of that. And I can plug that into my power equation. So power is work over time. So the work, 2,429 joules divided by a time of 4.2 seconds. That gives me 578. I guess this technically I should probably include those zeros since those are significant, and that's going to help us with rounding our answer. So 578.3 watts. This unit is a little, sorry about that, a little confusing because the unit for power is a W, symbol for work is a W. We have weight popping up every now and then, that's a lowercase w. So you do really need to pay attention to, for this unit, what exactly are your givens that you have and that you're using. All right, so those were just a couple practice problems just to get you hopefully feeling comfortable with the practice problems that are posted in the Google Forms. So now that you've taken these notes, The homework for the day was to work on the questions in the Google form. So that'll be the next thing that you'll want to do, the next step here for you. If you have any questions, I am going to, of course, be in my virtual office hours, so feel free to contact me there, or of course you can send me a quick email. But hope you all have a good day, and I'll see you soon.